This is the first lesson in the polynomial functions unit. The rest of this course, we're going to start looking at functions, equations, graphs, algebra, that kinds of things. So we're pretty much done with shapes. That was on your midterm exam. Hopefully that went well for you. The second exam, or final exam, will be just on this half of the course. So polynomials, algebra, exponential, and logarithmic functions. Before we get started on that, we've got to talk about what is a function. And this should be mostly reviewed from grade 11 material, but just in case there's some new things here, we can talk about those things. Okay, so two big ideas today, relation and function. A relation is any graph, any pairs, any relationship between two different types of variables. In there, functions are special versions of those. In this case, no two different ordered pairs have the same x values. Okay, so this is our idea of input and output machines. When I input an x, I have to get a distinct single output every single time for something to be a function. If sometimes I put in 2 and I come up with 4, and I put 2 in again and come up with 7, well, that's not a function. It's something else. It's just a relationship happening there. So taking a look at this first example here, the blue one's a function, because for every x, I've got 4 different x's. Okay, I never have a repetitive x. I have a function. Whereas the second one, I see it when I put in a 3, it came out with a 5. I put in a 3 again, it came out as a 1. Okay, that pair of ordered pairs has two x's that produce different y values. That would be just a relationship. Okay. We can we can create lists of ordered pairs. We could also create mapping diagrams. That's another way of showing a function or not a function. A mapping diagram is some sort of rule that shows sets of numbers. The set on your left would be your x values. So these would be your x's. The set on the right would be your y values. So when I input my x's and I output them, there's some sort of rule going on here. And in this case, it happens to be the rule is that y equals x squared. So when I square negative 2, it comes out to 4. I square negative 1, it comes out to 1. I square 1, it comes out to 1. These are functions because every x produces a y value, a single, distinct y value. Some of you might be saying, well, what about these ones in the middle right here? These have the same number, right? But that's the same y value, and that's okay. It's okay to have the same y value. You just can't have the same x value going to two different y's. Whereas in the second graph here, I input a 1, and it produced a 2, and it also sometimes produced a 4. That's the problem. That's why that's not a function. Okay? Each x has to produce one single distinct y for something to be a function. Okay. Graphically, okay, so we looked at some ordered pairs, we looked at some mapping diagrams. Sometimes you already have the graph made for us. To tell something's a function from a graph, we use the vertical line test. You may have heard of this. If you haven't, this will be something new, but hopefully you have heard of it. Okay. If you were to draw a vertical line through your graph, and it only passes through your equation, your picture, your graph once, that's a function. And what that means is, every time I put in an x value, I only got one y value. So for example, in this first one here, if I were to draw a vertical line right down my graph right here, okay, I only go through the graph one spot, right there, one time. And it doesn't matter where I move this line to, I still only go through the graph once. Okay, it does not make a difference. There's only one point of intersection. So this graph here is a function, for sure, for sure, for sure. Okay. The second one, I tried drawing a graph over here. Well, let's say I drew my graph, I don't know, right here. I've passed through the graph once, and I passed through the graph twice. At this point, where x is 3, I have a value of, let's call that 1.5. But sometimes I also have a value of 3 and negative 1 point, looks a little bit bigger, 1.8. You know, I can't do that. I can't have the same x value producing different y values. So this one is not a function. We would call this one a relation. And I don't need to actually make a list of points. That's not our objective here. Just the fact that it passed once, twice through a graph tells me that this thing's a relation. Okay, so you try a few so you can figure out function or relation. Yeah, look at C. I draw my line here. Well, that looks pretty good. Only goes through the graph once. However, when I move it over here, once. Over here, it's twice. That's a problem. And this one obviously is a relation. I have to be able to draw that line anywhere on the graph to produce a functional relation. And you try D, draw my line right here, move it around a little bit, once. Over here, it's going down to the right. It's getting a little bit wider, a little bit wider, a little bit wider. It might look like it's passing more than once, but it actually is only once. That's a function. Okay, so objective number 1 today. Can you identify the difference in a relation and a function? And hopefully by now you can, either from ordered pairs, a mapping diagram, or some pictures. Second part of today, function notation. Once we've identified things as functions, we use function notation to start working with them. Function notation is this idea of f and then in brackets x. It does not mean f times x. It means f at x. Okay, so for example, f in 2, we'd say, well, what's happening when x is 2? This f at 2 part basically means the same thing as a y value. We just don't use y's when we're talking about functions. We use f's for function notation. Now, it doesn't have to be the letter f. This first example here, the height of a cannonball in meters after t seconds, I used h and t. Okay? H at t. What is the height at certain times of t? H at 1, so what's the height after 1 second? H at 2, what's the height after 2 seconds? H at 3, what's the height after 3 seconds? It's a way of showing information without having to write out a lot of words. I look at that and say H3, okay, I'm figuring out the height after 3 seconds without having to use those words, right? So let's try a couple. I got a graph here, the graph of a function. Using the graph, find f at 2. Okay? The 2 is your x value. Your x value of 2 is right here, right? So on the graph, that's that dot. So f at 2 equals, what's the y value? -1. This is a way of saying that the point 2 and -1, because that's your y, is on the graph, without actually writing out all those words, right? Okay, f at -1. -1 would be right here, so my point is right there, and that value would be 1. I'm saying the point -1 is part of this graph. F at 0, that would be 3. We can do some operations. F at 2 minus f at -2. We'd figure out 2, which we've already done here in part A, so I'm going to take that down here, right? -1 minus, oh, what's happening at -2? -2 is right here. Right, that value there is 1. So -1 minus 1 gives me -2. Okay, reading stuff off a graph, finding different points on a graph by using function notation. We can also do function notation algebraically. If I want to do that, I'm going to replace the x with the value that I'm given. Okay, so I've given some sort of function. F at x equals 3x plus 1. If I want to find f at 3, I'm going to replace the x with 3. So I did it on the left, I have to do it on the right. Whenever I see an x, it becomes a 3. Well, 3 times 3 is 9. 9 plus 1 is 10. Okay, I do not do anything at all with the left-hand side. Because remember, that's my x value. Here's my x. Here's my y. I'm basically saying the point 3 and 10 is a point on this graph without actually going through with all those words. Okay, you guys can try the next one if you want to. F at -2. 3 times -2 plus 1 will give us -6 plus 1. It gives us -5. The point -2, -5 is on this graph. Okay, f at 5 minus f at 1. So like we did with graphs, we can do operations between functions from equations. So I have to do basically 2 separate equations here, right? I'm going to figure out what f at 5 is, and then f at what -1 is, and subtract the 2. I can do that in 2 parts if I wanted to, or I can just put big brackets around these things. So 3 times 5 plus 1. There's f at 5 minus 3 times -1 plus 1. There's f at -1. We do each part separately. So in the first bracket, I'll get 15 plus 1 minus -3 plus 1. What's that going to give me? Well, that's 16 minus, this part over here is -2, and that'll give me 18. Okay. If I try the last one, I want to find 2f at 3. Oftentimes, people find that 2 a little bit confusing. So let's ignore it for a second. Would you know what to do for f at 3? Well, f at 3, I'd replace the x with 3. So 3 times 3 plus 1. I think we've already done this one, right? That was 10. But the question wasn't f at 3, it was 2 times f at 3. So what do? I take my 2 and I times it by f at 3, which was 2 times 10. I get 20. Okay, so operations within function notation. Okay. They can get a little more complicated. Sometimes we have multiple x's. This means we have to replace multiple parts. So if I have this function up here, this quadratic, and I want to replace x with -1, I can do that. Everywhere I see an x becomes a -1. Everywhere I see an x becomes a -1. So I had to do it twice. Hey, we can put this all in our calculator at once if you want to, or do bed mass. -1 squared is 1. -2 times -1 is 2. 3 times 1 is 3, plus 2, plus 1. I get 6. Okay, you guys can try the next couple. Same ideas. 3 times 2 squared minus 2 times 2 plus 1. 2 squared is 4 minus 2 times 2 is 4 plus 12 minus 4 plus 1 gives us 9. Hey, you don't have to show all those parts and pieces. It's fine if you want to put in your calculator the way it looks. Just be careful with brackets, especially when you have negative signs involved in things, right? Okay, I got one of those multi-part ones. F at 3 minus f at -3. So we're going to do those big brackets. And we're going to use our equation. Okay, what was it? 3x squared. So 3 times 3 squared minus 2 times 3 plus 1. That's my first bracket. Minus the next big bracket. 3 times -3 squared minus 2 times -3 plus 1. I'm just going to move this letter d out of the way for now. Okay. We do each part separately and we put them together at the end, right? So, exponents first. 3 times 9 minus 6 plus 1 minus 3 times -3 squared is also 9, right? 2 negatives make a positive. Plus 6 this time, plus 1. And expand my brackets. 27 minus 6 plus 1 minus 27 plus 6 plus 1. And in the first bracket, I'll end up with 22 minus. In the second bracket, I end up with 34. And 22 minus 34 makes -12. Okay, operations between functions. All right, last one here. I want to find letter D, just move it down to the bottom here. 3 at f minus 1 plus 2. And we said earlier, you get all these weird things here, ignore them for a second. And you say to yourself, okay, what is f at -1? Now, I think we've actually done this one before, right? F at -1. Way back up here, we said f at -1 was 6. Okay, so I know that f at -1 is 6, which means when I go to do this operation stuff, this is the same as saying 3 times f at -1 plus 2, where f at -1, we just said, all this can go in here. F at -1 is 6, so 3 times 6 plus 2. Or in other words, 18 plus 2 is 20. And that's some operations with functions. Hey, one left, sort of an application idea. During the first 20 hours of an experiment, the growth rate of bacteria follows this equation. What's the growth rate at 4 hours, and again at 15 hours? Okay, so this is our idea. We're going to be working with equations in this unit. We have to be able to deal with functions. So I need to figure out what's happening at R at 4. And again over here for part B, R at 15. So we're going to replace every time I see a T with 4. Every time I see a T with 4. I'll move this one away for now. Everywhere I see a T with 4, and everywhere I see a T with 4. This time I'm just going to punch it all in my calculator. I end up with 10.72 bacteria per hour. Okay, and that's so we can do some function notation.